Good morning. Here we are back in Physics 4B lab. Today we were going to be doing a measurement of the electric magnetic force constant. Now that's kind of a funny way to say it. It's the force constant for all electric effects and magnetic effects. It turns out the electric force and the magnetic force are really all part of the same force. So what we're going to do today, let me grab a couple of items here. Is this. What we are going to do is we're going to get some current going through a solenoid. So we're going to get a solenoid-shaped device, a wire coil, and we're going to generate a magnetic field. So by having all of those charges in motion, we end up generating a magnetic field. Now, on the other side of that effect, we're going to have current also traveling along the perimeter of this plastic blade. And what we're going to do is we're going to take the plastic blade and balance it inside the solenoid. So I have two different currents going on. I got the current that's looping around like this in the solenoid, and then I got a current that's traveling along the perimeter. Now, what we've been seeing in chapters 27 and 28 with magnetic forces and magnetic fields is that there's going to be forces acting between these two sets of moving charge. Now, let's take a look and see. So from the side, it's going to look something like this. Now what's going to happen is when we turn the current up, the blade inside is going to get pushed down as a result of that magnetic force. So here is a top view, let's call it. So we'll say this is a top view looking down on this whole setup. So I've got a solenoid set here, and I've got this blade with current inside, and we're going to run the currents in directions so that inside the solenoid there's going to be a force pushing downwards on the end of the blade. And so with that force pushing down, this other side out, the portion outside is going to get lifted up. Now what we're going to do is we're going to put a little bit of mass. We'll put some weights on this side and balance it out. So that's what this diagram is referring to right here is, well, as we turn up the current, we're going to pull this side down, but that's going to be balanced by a mass on the other side. Now, the easiest way to carry out this balancing act is actually this. What we're going to do is we're going to put little bits of mass on one side. That's actually going to it's going to rotate this side downwards, and then we can adjust the current. So it's easier to start with a fixed amount of mass and then use just the right amount of current to balance that out. And so we'll start with placing a mass. Here's what our data table says. We're going to start off with a certain amount of mass on this side, and that's going to generate a gravitational effect that's going to pull one side down. Now, the force that we calculate on the gravitational side, we're going to balance that by using a magnetic effect. We also have the lever distances here that balance out. So some of you may be going, well, wait a minute, isn't this really a torque problem? It's not just balancing forces. Don't we have to include lever distances in the effect? And you're absolutely right. So what we've done on here is we've put these balancing pieces halfway between the two sides. So the magnetic force is going to happen right along here where the current is traveling. And so we need to place the masses so that the masses are equal distance away as the magnetic force is. So we'll make sure that this lever distance matches the lever distance on the other side. And so in our torque equation, the lever distances cancel out, and it just comes down to balancing forces. All right, so that's the idea. Now, it turns out that the magnetic force that we generate is not very big. It's not much of a force, and so it doesn't take very much mass. In fact, the amount of mass that we need is, it's going to be like a couple centimeters of masking tape. So now around here, let me see if I can track this down. Here is, let me bring this over. Here is here's one of the pieces of masking tape I was using in doing some of the measurements. It's about 1 centimeter of masking tape. And if I put that on the scale right here to find out how much mass we've got, it turns out it's massless. This is such a low amount of mass that it didn't even show up anything on the scale. So that's not going to work. The scale's not sensitive enough to read that portion of mass. So what I did instead is this. I got out a meter stick, and I took an entire meter of masking tape. Now, I measured it a little more carefully before, but what I'm going to do then is take this meter of masking tape. I'm going to stick the whole meter on the balance here. I'm going to zero this out. I put a whole meter on here, and it says 2.05 grams. So what I can do then is, that's very close to 2 grams, but 2.05, we'll write that down. So now what I can do is I can get out some scissors, and I can cut, I'm going to cut a 1/2 centimeter, and then a meter, and 1.5 centimeters, and so I'm going to do different lengths of tape, and they're all going to be, you know, a few hundredths of a gram. Okay, several hundredths of, well, a few hundredths, like 1, 2, 3, 4, 5, 6, something like that, hundredths of a gram, kind of like this one that I cut from before. And that's going to be enough mass to, so we're going to put, like, you know, these few hundredths of a gram of mass on one side, and then we're going to use a current, adjust the current, until we bring it back into balance. This is a top view. So here is the blade, and the blade is designed, if you take a close look at this, you can see that from these contact points, which is how we're going to get the current in there, the conductive material only goes in one direction. So whatever current we have, all the current goes just one way, which means that if I put this blade in the correct way, then I'll get current traveling through here. But if I accidentally get it backwards, all the current goes out here, and I'm not going to have any effect at all. So that kind of tells us we've done something wrong if there's no effect happening at all. And then I'm going to use the right-hand rule. So I set this up so that the current comes through. Let's see, I'm imagining the magnetic field inside the solenoid is in this direction. So if I have the magnetic field inside in this direction, and a current goes through, I can use a right-hand rule for current, and the force is going to be downwards, and that's the direction we want. Again, this is something we can check, because once we get the setup going here, if instead of lifting up that edge of the blade, if it gets moved downwards, we've done something backwards. So, you know, we can watch the orientation of the currents to make sure that we're getting the correct orientations. So let's see, I've got the gravitational field equation. I've got a force equation from chapter 27, which tells us how much force we should have based on the magnetic field. Now we're going to use that in the reverse way. And when I say in the reverse way, what we're going to do is calculate the magnetic field by measuring the force and then dividing through by the current and the length. Now remember, we're only going to get a force along that short distance, because if the magnetic field here is running along the length of my solenoid, right? So I got the magnetic field oriented in this direction. Well, if I have a current oriented in the same direction, that's not going to experience a force. And if I have a current oriented in the opposite direction, that won't experience a force either. It's only this short distance from this edge to this edge where the current is moving perpendicular to the field. That's the only length where we're going to actually have a force. And it's not even that entire distance, because the current is going to tend to take the shortest distance here. The current's not going to go out around these edges. So in any case, what I ended up with was, I think it was 2.2 centimeters is the distance along which we're going to have a force actually occurring. So it's only a couple centimeters of distance along which we'll actually have a force. Big L is going to be a really small number, and I guess we got to start getting some of this stuff listed. So big L, 2.2 centimeters. And that came from getting out some rulers and making the measurements. So let me grab a ruler too. So I got a ruler here, and I'm measuring the distance along there, trying to get a reasonable sort of average. So that, everything is set up here. So let's do a quick review here. We're going to put a little bit of mass on the end here. That's going to tip this part down because of the force of gravity, which is mg. Now what we're going to do then is we're going to turn the current up until this comes back to balance again. And when it's balancing, then the force is going to be magnetic on this side, given by ILB. I can solve that for B. So by knowing the force and looking at my ammeter to measure the current, and by using this distance, 2.2 centimeters, we can determine how large the magnetic field is that we've set up. All right, now with a solenoid in chapter 28, we've learned that the formula for determining the magnetic field of the solenoid, 4 pi k over c squared n over L times I. This formula also is going to get flipped around. We're actually going to be doing this. We're going to take this formula for the solenoid and flip it around and say, well, K is going to be given by B times C squared times L over 4 pi N times I. So once we know what the magnetic field is, all these other things can be measured, and we can determine what the electric magnetic force constant is. We can come up with a value for that. So here's our data table. We want to calculate how much force, read off how much current we're using to balance it, calculate the magnetic field, and finally calculate the force constant. Now here is our setup. We're going to have a power supply. We have a variable voltage. It's DC, so we're going to have a variable voltage DC power supply, and that is going to generate our current, and that's how we're going to be able to control how much current we've got. And we're going to turn this up until everything balances out. Now, the current is going to go through an ammeter. The ammeter is going to tell us how much current we've got. The current is going to go through the blade that runs through the center of this setup, and the current's going to go through a solenoid. So it's the same current everywhere. So the current that is generating the magnetic field in the solenoid is the same as the current that's going through the blade. So there's just one current to measure, and that same current is going to be traveling throughout the circuit. Finally, we're going to have a results table. There are definitely accepted values for the electromagnetic force constant, 8.99, 10 to the 9 newtons, meters squared, coulomb squared. We're going to compare our measured value with that and then calculate a percent difference. So we'll see. There's a couple things here that are going to give us issues. The ammeter is pretty reliable. It's kind of hard to tell exactly when we're back in balance again. But we'll take a look at the close-up settings and we'll get a better idea about what kind of things we might be running into. So here's the experimental setup. So what we've got is I have an ammeter right here. I've got that set up so we can start reading out how much current. We've got our variable voltage supply right here. And so this, let me just show you, this can be turned on. And then I have a control here that can vary the voltage from 0 to 5 volts. I'm also going to turn the ammeter on. There we go. So the ammeter is now up and running. And then what we've got here is, let's take a look at how this is all wired. So everything's in series. The current goes through the ammeter, goes through the solenoid. And then what we've got here is that blade inside. Let me move this brick out of the way. And I was very careful. I got in and made sure that the blade is free to rotate up and down inside here. That's important. We don't want it to get stuck. And then what the brick is doing here is it's giving us a reference. So what I've done is I've gotten some tape out, some masking tape, and I've got the tape set up so it's showing the current balance point for this blade. Now what I'm going to do is, here is my 1 centimeter of masking tape. I'm going to set that on top here. Now remember, I've got to match distances, and you can see that it's now, it's oscillating back and forth a bit, but you can see that it's dropped due to that. So it's not much mass, but it's enough to drop it significantly. Now what I'm going to do is I'm going to vary the current. So I'm going to vary the current, turn up the current here, and I'm going to bring that current up, and at the same time, so here I am increasing the current, and we should see this thing rising. There we go. So here it is coming back up. Now I got to balance the current out. And there can be little oscillations, or it can be actually pretty significant oscillations that come up. So what you can do is you can reach in and just damp that out. All we're really having to do here is make sure that we're back at the same equilibrium. And so let me settle this down. So we're starting to read some current here. So we're at 1.3. Now this is oscillating too. Actually, I have a lot of shade here. So this is oscillating too as this goes back and forth. I'm going to try and damp this out. So let me try that one more time here. Let me see if we can damp this out. And sometimes the best we do is just a little bit of oscillation that's taking place. And so this was settling in at 1.335 amps. and the oscillations had died down some. But that's pretty much it. So that's what the experiments consists of. And then what we'll do is we'll take out that 1 centimeter of tape, and what we can do is we can replace it with some additional different sizes of tape. So we're going to try a variety of different tapes, and we'll see what the numbers work out to be. I had done a run earlier with this 1 centimeter, and here are the values that I ended up with. And so I had ended up with a K value of 10.5, 10 to the ninth, a little higher than the accepted value, kind of in the ballpark, but you can see that, again, the oscillations are going to become a bit of an issue here. And so it takes some time to play around with these and damp those out so that we can get a reliable current measurement. All right, we're going to go after one of those fundamental constants of nature. No one knows why the electromagnetic force has, the force constant has the value it's got, but we're going to get a measurement of it.